Hello and welcome to the next video. In this video we are doing an overview of the physics acting upon the aircraft in flight. Lift, drag, thrust, weight, airflow, angle of attack, and stability in flight with different center of gravity points. So without further ado, let's get stuck in. Lift, weight, drag, and thrust. These forces never leave you, from the moment you lift off the ground to the time your bulk settles back down on terra firma. Because of weight, you need lift, and because of drag, you need thrust. Flight is all about balance and having equal forces acting upon you. The moment an unequal force begins working on your aircraft because of an instability or unseen circumstances, problems rapidly manifest themselves. A great example is Concorde. To maintain stable flight, Concorde had to be continually pumping its fuel from one internal tank to another, moving its fuel around the aircraft to maintain a delicate center of gravity. If it did not do this, the aircraft would simply fall out of the sky. Let's look at a standard cross-country cruise in level flight in the C-172 and see how different loadouts and situations affect the aircraft. Equilibrium. In the cruise, when an aircraft is flying along at a fixed speed and altitude, the lift being generated is equal to the weight of the aircraft. So, for instance, if the aircraft is 1,063 kilograms, then we can assume that there is 1,063 kilograms of equal and opposite lift, causing the aircraft to fly forwards without descending or rising. Following this same theory, if the aircraft is producing, for instance, 60 kilos of drag as it's pushed through the air, then the engine must produce an equal and opposite thrust of 60 kilograms to keep the aircraft at its cruise speed, without it slowing down or speeding up. This is a stable cruise state, and everything following on from this will be a state of change. Lift and factors affecting lift. Lift is created when air flows over and around a wing. The word wing can be applied to an airplane, a helicopter, or even a sailing boat. These are all designed to harness the power of the air to create lift. The airflow meeting the wing is often referred to as the relative airflow. For the purposes of this video, lift acts at about 90 degrees to the relative airflow, and the angle at which the relative airflow hits the wing is called the angle of attack. Now, there are a number of things which influence how much lift a wing produces. See Part 4 on control surfaces. But the two main things a pilot can control is airspeed and angle of attack. Your airspeed is controlled by your engine. The more thrust your engine is producing, the more air begins flowing around your wings, and the more lift is produced. But here is where angle of attack comes in. The more angle of attack, the more lift, until a certain point, however. For a light aircraft like this, the range of lift comes between -2 and +14 degrees of angle of attack. Typically, in cruise, the angle of attack will be around 4 degrees. Importantly, if an aircraft is flying very fast, only a small amount of angle of attack is needed for level flight. But if the aircraft is flying very slowly, then a greater amount of angle of attack is needed to maintain level flight. This concept of angle of attack is an important one to grasp. In a light aircraft like the C-172, there is no gauge to display how much angle of attack you are currently using, and it's not necessarily the same angle as the aircraft's pitch attitude. However, changing the aircraft's attitude does alter the angle of attack in the same sense. For instance, pitching the nose down reduces the angle of attack. Drag. Drag is the resistance created when trying to push an object through either a liquid or a gas. At sea level, the air pressure is greater than at 35,000 feet. That's why airliners today will fly at the optimum altitude to experience the least drag to create the most efficient cruise conditions. There are two elements of drag: parasite drag and induced drag. Parasite drag is with you every step of the way. The faster the aircraft moves through the air, the greater the parasite drag. Going back to our example of Concorde, at its cruise speed of just over Mach 2, the aircraft's skin actually heats up and expands because of parasite drag. The whole aircraft actually expands so much that they need to develop extra stretchy carpet for the passenger cabin, and in the cockpit there is a... Anyway, I digress. So, long story short, your total airframe drag is your parasite drag plus your induced drag. Induced drag is the kind of drag your wingtip will make, causing a tip vortex that spirals out behind you as you fly. This is why many airliners today have winglets or sharklets to reduce this aerodynamic effect and burn less fuel. Stability in pitch, roll, and yaw. Aircraft stability isn't just a question of lift, thrust, drag, and weight. There is a delicate balance that needs to be maintained with regards to the center of gravity. This balance will ensure the aircraft maintains stability in the three axes of movement: pitch, roll, and yaw. Let's look at pitch to begin with. To maintain stability in pitch, we should arrange the forces in such a way that weight pulls through a point, the center of gravity, that is ahead of the center of the lift force. The sum total of these two forces produces a downwards pitch motion, as they are essentially trying to rotate the aircraft, if you are looking from the side view. As this is happening to the aircraft, there is another simultaneous force at work. This is the thrust and drag. Thrust is happening to propel the aircraft forwards, and drag is pulling backwards, trying to slow the aircraft down. You will see that, again, these two forces, when added together, will create a turning force on the aircraft. But this one is working in the opposite direction to the previous force, which means it helps to cancel it out. It does not, however, manage to do so completely, and that's where the tail plane comes in. The tail plane actually cancels out the remaining pitch down motion, because the angle of attack of the tail plane causes it to raise the nose again. Now, I know that's all a lot to take in at once, but if you put it all together, you get an aircraft that's able to fly in a straight line in a stable manner. If a wind gust hits the plane, it might knock it off course slightly, but because the aircraft is aerodynamically balanced, it will always want to settle back down into its original state and level attitude. This is why it's so vitally important not to load an aircraft so that its CG is outside the operating limits as stated in the aircraft's manual. Also, imagine that the CG is the beginning of a lever, with the end of the lever ending at the tail plane. So as you move the CG backwards, you are shortening that lever, and therefore reducing the effective leverage that the tail plane has to correct unstable flight. Let's look at roll stability. This is largely provided by the angle of the wings to the horizontal, or the dihedral angle. When an aircraft is flying in a straight line, but at a slight bank, it will always want to gradually roll back level again. This is because the two wings are both angled slightly upwards as they stretch from the fuselage to the wingtips. This means that in a bank, the angle of attack to the airflow of the higher wing is less than that of the lower wing, causing the higher wing to produce less lift and want to drop. For the C-172, the dihedral is not so pronounced in comparison with that of, say, a Piper Cherokee, which has a low wing configuration. A high-wing aircraft has its CG below the point of lift. With the CG effectively hanging below the point of lift, there is less dihedral needed for the wings to create stability. Finally, let's look at yaw stability briefly. This is produced purely by the fin at the back that sticks out into the airflow if you yaw the plane. The angle of attack on that surface creates a turning force that brings the aircraft back to centered flight. Thank you very much for watching, and in the next video we will be covering a series of flight exercises such as correct cruising, climbing, descending, and situational awareness.